Hello, guys. Can you hear me?
Yes, sir.
Thank you. Thank you very much. So we are working on chapter 5, protein function. And so you saw the practice test. Hopefully you will have a better idea of what to expect on the actual test. Well, also what I will do is I will actually make sure you make use some of the text to prepare for the test. So I'll send you some pages, specific pages to read. All right. Any questions about anything in this class? Before
The only question I had was I wasn't able to find the chapter 5 slides on Canvas.
Yeah, I uploaded them this morning, but I forgot to click on the copyright button, so it wasn't released. I just did it, so now it's available. I'm sorry.
Thank you.
Mm-hmm. All right.
Will the exam be open all day or just the time of our class?
Yeah, you have to take the exam during the class period. Yeah, so I'm not going to be doing any proctoring or anything. So my way of avoiding cheating on the test would be first is that I make the problems in such a way that it's going to be very hard to Google them, right? So like I will not be quizzing you on known things. It'll be more like thinking. Yeah, I'll ask you to think about something and using your knowledge and provide me the answer based on that. And secondly is also the time limit. So I have to make sure that you have enough time on the test, but not the whole day, right? Not the whole day, because if you have the whole day, then it's very tempting to look things up. So make sense?
Yes, thank you.
Mm-hmm. The exam is going to be multiple choice. All right. Protein function. If you can't see the slides, let me know. The slides are open. All right, so what do we expect to take home from chapter 5? So this is all going to be about interaction between a ligand and a protein, right? So what we will find out is that intermolecular forces that are used by proteins to fold into three-dimensional shapes and forms. These intermolecular forces can also be used to describe ligand binding to proteins. So here we actually killed two birds with one stone, and it's gonna save us a lot of time on learning these concepts. We will look at some quantitative and graphical modeling of protein-ligand interaction. So specifically the strength, right? So how do we compare different ligands between each other? Which ones bind strongly, which ones don't bind strongly, and why is it important? We will look at globins. So these are proteins which interact with oxygen. And specifically, we will use hemoglobin and myoglobin as our two models for this kind of interaction. Physiological regulation of oxygen binding. very important, right? So when you have oxygen transport protein, you want to be able to, for the protein, when protein goes into the lungs to pick up oxygen and brings the oxygen into the tissue, you don't want your protein to be bound to oxygen with the same affinity, right? Sorry, my cat is going crazy. So you want your protein to have very high affinity when it's in the lungs, so it can carry as much oxygen as possible into the tissue. But once it gets into the tissue, you want all that oxygen to be released. So there must be some kind of physiological regulation of that, right? There's something in the tissue that is absent at the lung, in the lung. And then we'll talk about mechanism and control of antibody-antigen interactions, so different model, and mechanism of muscle contraction and regulation of that. All right, so globular proteins. So they have lots of functions. So this is just a general overview of what they do, right? So myoglobin, so we just talked about it. Storage of oxygen. Storage not transport, but storage. And primarily in the muscle, right? That's where oxygen is needed. If you need to perform hard work, right? So and you need to run very fast, and the amount of oxygen that's going to be transported from the lung into the muscle is just not going to do it. Then myoglobin will provide you with extra oxygen required for the muscle to work. Ferritin is a protein, which is also a storage protein, but it stores iron. Iron is very important in a biological system, particularly because of its redox properties, right? It can undergo reduction oxidation very easily. It's also very important for the generation of reactive oxygen species, so it could be quite dangerous to have lots of iron. It's required, but could be dangerous. And so it's important to have some kind of system to store iron and regulate how much iron is actually accessible, right? In fact, ferritin, one molecule of ferritin contains up to 4,000 iron atoms. So very well, so the protein that has evolved to contain so much iron. All right, so for transport, so here we're going to talk about hemoglobin. We'll talk about serotonin transporter. Anybody knows what serotonin transporter does?
It's part of it's a neurotransmitter, right?
Neurotransmitter. And where does it transport serotonin from and to?
It's in the brain, I think. I know it has to do with like happiness, sort of, because I know a lack of it leads to depression. That's all I know.
Right. So here, if you have a synapse, right? And the action potential arrives along one of the, So this will be presynaptic neuron. Presynaptic. This will be postsynaptic. Postsynaptic. And then when the action potential arrives, neurotransmitters such as serotonin will be released into what's known as synaptic cleft. And then how does serotonin get back inside?
Is it like reuptake?
Reuptake. So we need serotonin transporter, which will bring it back into the presynaptic neuron and package serotonin into vesicles ready for the next action potential to arrive. Yeah. So one of the key globular proteins, specifically transporters in the brain. Okay, defense against pathogens. So antibodies are globular proteins, cytokines, muscle contraction, actin, myosin, biological catalysis, chymotrypsin, lysozyme. So a lot of different globular proteins performing a variety of functions. Any questions? So you can see there's actually a lot to study for us, but we will focus primarily on these two, hemoglobin and myoglobin, sort of classical transport proteins, which have been studied for many, many years. Okay, so ligands. So ligands interact with other proteins, and so the molecule that binds to a protein is known as a ligand. And generally, it's a small molecule. And the region in the protein where this ligand binds is called the binding site. Now, if your globular protein is an enzyme, it can also be called active site. Active site. If enzyme. So ligand binds, we have same non-covalent interactions that dictate protein structure. So just like I mentioned to you earlier, right? It will be hydrogen bonding, it will be hydrophobic, it will be electrostatic, van der Waals interactions, polar. And so my question for you, why is it important that these interactions are non-covalent? So why can't I make a covalent bond between the ligand and the protein?
Because you want the bond to be weak?
I want the bond to be what? Weak?
Yes.
Why do I want it to be weak?
So that it can come back apart, so that you don't want them to stay put together for longer than necessary.
Right. So I don't want to kill my protein with my ligand, right? So in general, this is something which is called turnover number. So we will talk about that in the context of enzymatic catalysis. But basically, it's the number of molecules which the enzyme or the protein processes within 1 second. It's called the turnover number. So you don't want this turnover number to be 1, right? Because proteins are large molecules, they're so precious, and you don't want to kill 1 molecule of protein with 1 molecule of ligand, right? So you want the protein to process as many molecules as possible. So in general, you want these processes to be non-covalent, unless, can you think of a scenario where you do want this process to be covalent? Sometimes you want it to be covalent.
And like antibodies?
Antibodies? And why do you want them to be covalent in the context of antibodies?
So that they remain bound to the antigen?
Okay, that's one good. I agree. Anything else? How about the discovery of an anti-cancer agent? What if you have a bad guy, a bad kinase that's gone out of control? Then you want to kill it, right? You want to kill it with as few molecules of drug as possible. So then a covalent binder would be nice, right? So that's another possibility. All right. So consider a process in which a ligand binds reversibly to a site in a protein. So here's our protein, here's our ligand. So some kind of rate. So A stands for association, D stands for dissociation, right? Association. There it is. Association rate constant and dissociation rate constant. And so after a certain point, you mix these two together. The two reactions, which are both expressed using these rate constants, rate laws. So this is reaction rate times the concentration of the protein times the concentration of ligand, right? So this is the forward reaction. And the reverse reaction is the dissociation rate constant, right? Times the concentration of the protein with the bound ligand, When these are equal, we say that the process has achieved the equilibrium, right? And you can express it using these equilibrium constants. So now this is association, equilibrium constant for association, and equilibrium constant for dissociation, which is the reciprocal of that, right? So so let's how do we compare different ligands among each other, right? In terms of there are different ways to do that. So let's do it in terms of the bound fraction, because after all, the functions may be different, right? But what's common among all these processes is that we want our ligand to occupy as much time as possible on the protein. Okay, and that will be the bound fraction. So, right, so at any given time, how much of this protein is actually bound to the ligand? So this letter theta is going to be the fraction of occupied binding sites, right? And we're going to express it using this formula. So theta, basically, so this is the amount of protein bound to the ligand in the numerator. And the denominator will have the sum of the amount of protein bound to the ligand and the amount of protein that still remains free. Yeah. So then we plug in, so we solve this for PL. So we plug in, we're going to substitute PL, basically protein ligand complex concentration. We're going to substitute that. If you pull these on this side, we're going to substitute with KALP and then eliminate PL. As we do that, we rearrange, we get this expression. P is going to be canceled out. KA is going to be added, right? And then we have this simple expression. And remember, KA is the reciprocal of KD. Right? And so this is our final expression. So the bound fraction will be the ligand concentration and the dissociation constant. So what does this tell us? Two things, I think. Well, to tell us more than two things, but two things that it's telling me right away. One is that the maximum possible number for theta is 1. Makes sense. It's a fraction, right? And obviously, you can achieve that if your KD is close to 0. So, which tells you the smaller the dissociation constant, the higher the amount of the bound sites, right? So, so the ligands with high affinity will have low KD values. And the second thing it tells me is that if my theta can be expressed like so. In other words, if my KD is the ligand concentration, then theta equals 1/2. Equals 1/2, right? So what this tells me that KD is the ligand concentration at which half of all the binding sites are occupied. And it can be easily found using this curve.
What are those units on that y-axis?
Yeah, so this is theta. I don't know what this y is. Why is it y?
Oh, so it's supposed to be theta. Okay. I thought it was like gamma. I was like, where did that come from?
Yeah, it's kind of strange. Why is it y? Does anybody know? Why is it not theta? Okay.
It looks like in the book there was a part where it was saying Y equals the binding sites occupied over the total binding sites. So I think it was using a Y in the book there, and that's associated with that image there.
Mm.
Yeah, it's the fraction binding sites occupied divided by the total binding sites.
Isn't that what theta is?
Is that PL divided by PL plus P? Is that theta? Because isn't theta L? Okay,
Yeah, anyway, math makes sense.
I gotta look through it slowly.
Yeah. Okay, so so example of this is oxygen binding to myoglobin. When the ligand is a gas, okay, so then you're going to turn L into partial pressure of oxygen, okay, and you can see here, now we have the actual numbers already, so these are not arbitrary units, and so then Kd becomes the partial pressure of oxygen at which half of the oxygen sites on myoglobin are occupied with oxygen. So that's P50. So
how did you get P50?
P50 is the same as Kd. Remember, Kd was the substrate concentration at which half of the sites were occupied. So P50 is the pressure of oxygen at which half of the sites are occupied.
Is that going to be like a constant whenever our ligand is a gas? We just put P50 there for Kd.
Yeah. Mm-hmm. Let me jump forward slightly, see what we have here. Yeah, we have it here. All right, so this is just a glimpse into the couple of slides ahead. So basically you can see already the heme, which is the prosthetic group, which will hold iron inside. And there are some, so this is just a preview of the structure of myoglobin, but we'll discuss it in much more greater detail a little later. But that's what myoglobin is going to look like. All right. Interaction strength can be expressed as association binding constant, right? Inverse molarity is the units. And then the dissociation constants, where the units are molarity. So dissociation constants are much more attractive if they are in nanomolar region, right? So majority of drugs on the market in nanomolar. Oops. In nanomolar. So so micromolar will give you a drug, but not a good one. So what that means is that you need much more drug to occupy the binding sites on your receptor. So the dose will go up. As the dose goes up, side effects go up, and the drug becomes more expensive because you have to manufacture it, right? And so on and so forth. Most drugs in nanomolar region. So interaction binding free energy. Keep all these parameters handy so that you know what they're equal to. Ka, Kd, right? So if delta G is expressed as using this equilibrium constant, then there's a negative charge in front of the log. If it's Kd, there's no negative charge in front of the log, and the magnitudes. And as far as binding affinity, so for non-covalent, so we just talked about covalent binding. Obviously, if you have a covalent bond, you're going to kill the protein or the enzyme. But you can actually you can kill the protein or an enzyme even with non-covalent bond if it's super strong. For example, biotin avidin, it's a type of interaction, which is a biological interaction that occurs in the region of 10 to the negative 15th. 10 to the negative 15th molar. So remember, how does this work? Millimolar, micromolar. What's next? As you decrease the molarity by 1,000 every time. Millimolar, micromolar. So what's 10 to the negative 9?
Nanomolar?
Nanomolar. What's next? What's 10 to the negative 12?
Is it picomolar?
Picomolar. And now, as you're thinking, for 10 to negative 15th, I'm gonna close the door to my kids' room. Philip, I asked you to be quiet. So what's 10 to negative 15th? Anybody? Femtomolar. FM. Okay, so so this interaction is, and in fact, is so strong that oftentimes people refer to it as a covalent interaction. So it can be deleterious. You know, it's strong, it's good, but there are situations when it's too good. So you can see, for example, antibody-antigen. Now there are some specific interactions. They all fall in the region of nanomolar. Remember I was telling you that's where a majority of things happen. So most biology happens in nanomolar region. Okay, that's when things are, when the biological interactions are strong enough, and yet they're still reversible. And you can see enzymatic interactions actually a lower affinity interaction. So here we have a micromolar and millimolar. Why do you think that is?
Can you repeat the question again, please?
So
Sorry, thank you.
interactions between, let's say, enzymes and substrates are in a region of micromolar or millimolar. So if I told you that majority of biology happens in nanomolar region, why the enzyme substrate biology happens in micromolar region?
The enzymes have to process a lot of different molecules, so they need to be able to make that change and then release it.
Yeah. So the enzymes have to be dynamic. They have to accept the substrate, perform the reaction, and let the product go. Remember, I told you turnover number. Very good. Turn over number. Right. So the number of molecules processed by the enzyme within 1 second. So you want them to be high. So you want the substrate to come in, reaction to be done, and product to be released. All right. All right, so specificity, lock and key model. So originally, this was proposed, you can see, even in the 19th century by Emil Fischer, who basically said that the enzyme or the proteins and ligands work like lock and key, right? So the lock is the protein, key is the ligand. If the key comes in, a wrong key doesn't recognize the protein, can get inside, and vice versa. So, so the key principle here is complementarity. Complementarity, and complementarity has to be in size, shape, charge, hydrophobic, hydrophilic, right? So you can see here, there is this shape, there's that shape, and they very nicely fit. But as time went on, we realized that things are not as straightforward as we thought, especially with the advent of the computational modeling. When people would pull up the structure of a protein on a computer screen, come up with the ligand that should fit as a key, and make the molecule, and the molecule doesn't fit. And so people started considering that actually it's not that straightforward, and that the conformational changes may occur as the ligand binds during the process of binding. And this adaptation is called the induced fit. And so basically, you can see here, both the ligand and the protein can change shape, right? So these come together, but once they bound, the energy of the binding compensates the energy which is required for these two to change their orientation, right? So it takes two to what's the word? To tango? Is that how it goes?
Yep.
Yes.
Yeah. So if both of them change their shapes, then overall that may result in energy gain. All right. Let me see where we are.
Is chapter 6 going to be in this test as well, or are we just going up to chapter 5?
No, that's it, just 5. All right. So globins are oxygen binding proteins. So now let's look in much more detail in how hemoglobin and myoglobin accomplish their function. So the biological problems. So protein side chains lack affinity for oxygen. Now keep in mind that oxygen is not very well water soluble. Remember, if I ask you to draw the Lewis dot structure of oxygen from general chemistry. Is that it? Is this the Lewis dot structure of oxygen?
Wouldn't the double bond be 4 dots like next to each other?
Yeah, I mean, it doesn't matter. I just represented it. I represented electron pairs as dashes. Doesn't matter. So, is this the correct representation of oxygen? Everybody's quiet.
Yes.
All right. So it turns out it's a correct representation in certain cases. In most cases, oxygen looks like this. So one of the electrons from the double bond uncouples from its partner and becomes a radical. So we refer to this as a triplet. Triplet state. Sometimes people say ground. So this is a relaxed ground state. And this one is singlet. Or excited state. That's part of the reason why oxygen is so reactive, right? Because it's a bioradical. In its ground state, it's a bioradical, and it's very good at oxidizing things. That's why it's used as a biological oxidizing reagent. So, but regardless, so here you need some energy. Here we need some energy. So regardless, do you see any charges? No, you don't see any charges. So oxygen is a non-polar molecule, which makes it non-water soluble. Non-water soluble. And so now protein side chains cannot help us very much because they don't have any affinity for oxygen. Now transition metal binds oxygen, but that would generate free radicals in in solution, right? So dangerous. Remember reactive oxygen species, ROS. Reactive oxygen species are very dangerous, and that they are generated when oxygen comes into contact with metals. Now, organometallic compounds such as heme are more suitable, but iron 2+ in free heme could be oxidized to iron 3+, dangerous reactive oxygen species. So biological solution. So how did biology come up with the solution? Capture oxygen molecule with a heme that is also bound to a protein, right? So several levels of kind of sequestration. We're going to capture oxygen with heme, and the heme itself will be inside of a protein. And so myoglobin and hemoglobin can bind oxygen via such a heme. So here's our heme. So this particular unit here is a heterocycle known as pyrrole. So heme is a assembly of 4 pyrrole units into one large ring. And so the iron will actually go straight inside. And so the nitrogens of the pyrroles will sit in one plane surrounding this iron. And there are 2 more bonds. There's a bond from the top, and there's a bond from the bottom. Okay, so you can imagine that one of them will be oxygen, right? And the other one can be some amino acid from the protein. And this is what it's going to look like. So here we have this proximal histidine residue.
Could you go back to the previous slide for just one moment?
Yeah.
Perfect, thank you.
So here's the plane of the porphyrin ring system, right? And so on this side, we're going to have the imidazole of the histidine. And on this side, we're going to have oxygen bound to iron. So myoglobin has 8 alpha helices. Has 8 alpha helices. Now they're going to be labeled as A, B, C, D, E, F, G, H. Okay. And you can see here is this histidine, the proximal histidine shown here, which will form a bond with iron. Now you can name this as histidine F8, which means that this histidine is located on this alpha helix F, okay, alpha helix F, and it's the number 8, it's number 8 amino acid from the amino terminus of this segment. Alternatively, you can label this as histidine 93, and histidine and myoglobin, hold on a second. I think it has 153 amino acids. Amino acids. And so this histidine will be amino acid 93 from the amino acid terminus, or it's amino acid 8 from the amino acid terminus of the segment F. Does that make sense? So there are 2 ways to label this histidine, but people refer to this as proximal histidine that will hold this iron in place in addition to the porphyrin ring system. Any questions? All right, let's move on. So there is a bad guy. There's a bad guy that can actually be a source of poisoning. It has been investigated. So porphyrin ring system, turns out that oxygen is not the best ligand for it. There is carbon monoxide, which is even better ligand for it. So carbon monoxide, if you draw the resonance structure of carbon monoxide, CO, like so. And remember, you can draw a resonance structure in which here you have a triple bond. Carbon monoxide. So very, very strong ligand. And it binds heme over 20,000 times better than oxygen, because carbon in carbon monoxide has a filled lone pair, electron pair, and can be donated to d orbitals on iron. It's this lone pair that I'm just drawing for you here. Right, it can be donated to the d orbital on the iron. But when you put the heme into protein, that will decrease the affinity for carbon monoxide, but it still binds about 250 times better than oxygen. It's highly toxic as it competes with oxygen, blocks the function of myoglobin, hemoglobin, and mitochondrial cytochromes that are involved in oxidative phosphorylation. So for example, if there's a fire, right? If there's a fire in a building and the firefighters just put it out, what are you not supposed to do? Do not go inside. Do not go inside. And why shouldn't you go inside?
Because you'd be breathing in the carbon monoxide instead of the oxygen.
Right. So so when the firefighters put out the fire, then whatever has not burned completely has not produced carbon dioxide. It has produced carbon monoxide. So at the end, when the fire is being put out, there's a lot of carbon monoxide being produced. And you basically die, right? So all your iron in your hemes throughout the body, in myoglobin, hemoglobin, and mitochondrial cytochromes will be occupied with carbon monoxide. And so when you put this in the protein, right? So oxygen, because of its lone pairs, remember, oxygen has lone, I just drew it for you. I just drew it for you. Two on this side, two on this side. And two on that side. And this one has a lone pair right in front of it, right? So now imagine that if you put this in a protein And the protein has this kind of pocket. This kind of pocket, which allows you to put the oxygen at an angle. But carbon monoxide cannot be accommodated with this, right? And so remember the pocket's gonna be like this. Right? So, so the protein protects us from carbon monoxide quite significantly. It's still a poison, but not as bad as it could be. So here is a...
I'm so sorry. Could you go back for just one more second? I'm so sorry. Thank you so much.
So, so you can see here, this is the three-dimensional view of oxygen bound to heme in myoglobin, right? And you can see here that, so this is the proximal histidine F8 on the other side. And yeah, basically just shows how oxygen binds, right, at an angle. Binds at an angle. All right. Now, so you probably already know that actually heme is responsible for the color of the blood, right, of the venous and the arterial blood. So it's a strong chromophore, absorbs light in the visible region, right? And so ferrous form, iron 2+ without oxygen, has an intense band at 429 nanometers. And so solid band is basically just the absorption, very strong band in the blue region. And so binding oxygen can be monitored by UV-Vis spectroscopy. And so deoxyhemoglobin, basically hemoglobin that does not have oxygen in it. And that's going to be in the venous blood, appears purplish, right? Because there's just not enough oxygen attached to the iron. And oxyhemoglobin in arterial blood is red, right? So you can actually monitor how much oxygen is being in the venous blood and how much oxygen is being in the arterial blood and how much of it is actually lost as it goes through various organs and tissues. Sorry, not lost, but how much of it is actually delivered to various tissues. All right, so the question is, could myoglobin transport oxygen? Well, partial pressure of oxygen in lungs is about 13 kilopascals. Sure, it binds oxygen well. Partial pressure of oxygen in tissues is about 4 kilopascals. It will not release it. It will not release it. And so the question is, so here's we've seen this curve before, right? So here's the partial pressure. And so you see, so compare 13 to 4. Now, let me use a pen. So 13 would be somewhere here, all right? So if we continue with this, oops. Why am I not? If you continue with this, and this will be partial pressure in the lungs, right? And if it's 4 in the tissue, it will be here. Four kilopascals. So, and then now obviously it looks much better than it actually is, but this is how much oxygen will be released in the tissue, right? So basically, the amount of oxygen will be released in the tissue that depends on the differences in the partial pressure of the oxygen in the lung versus the tissue. And we have very, very little. Does this make sense? So you want this gap to be as large as possible. So, so what needs to happen is the following. We need to have in the lungs, here's the lungs, right? Here's the lungs. We want, this is the partial pressure in the lungs is 13 kilopascals, right? And if nothing happens, if we don't do anything, then you can see that here in the tissue, nothing changes. The curve is such that none of it will be released in the tissue. But if there is a different affinity state, right? So for example, if the myoglobin have a different affinity state such that it has lower affinity for oxygen, then the curve may be like this. Maybe like this, and then you can see how much of it will be released, right? So basically, almost this entire amount will be released. So ideally, what we want to accomplish, we want the curve to be in the lungs like this. And we want to be the curve to be in the tissue like this. So in other words, we want to have two different myoglobins. We want myoglobin in the lungs, and we want myoglobins in the tissue to be different. One has high affinity for oxygen, the other has low affinity for oxygen. Does it make sense? And so, but we're dealing with the same molecule of myoglobin, so obviously, you know, we can dream about it, but we still have the same molecule of myoglobin. And so what nature has come up with, it has found a way for the myoglobin to undergo a transition. As it leaves the lungs, it's starting to lose the affinity for oxygen. And as it reaches the tissue, the affinity for oxygen is significantly lower. And you can see then this amount can be dropped off in a tissue, right? This amount can be dropped off in a tissue. And so how can affinity for oxygen change? So what can be done? So first of all, it must be a protein with multiple binding sites, right? So binding sites must be able to interact with each other. This phenomenon is called cooperativity. So there is positive, there is negative. So positive cooperativity, first binding event, increases affinity at remaining sites, recognized by sigmoidal binding curves. And negative cooperativity, first binding event reduces affinity at remaining sites. So in other words, as one molecule of oxygen binds, the affinity for the remaining oxygen molecules will change. Guys, you have any questions? This is probably the most challenging aspect of the material from today's lecture, is to understand this cooperativity. I think this this figure will do it for us. So so let's say so we are in this kind of situation, right, where there's no ligand, and the, let's say you have a protein with two domains, let's say, right? Protein with two domains, and there's a binding site. There's a binding site here, and there's a binding site there, okay? And the binding sites are not particularly well prepared to receive the ligand, okay? So you can see here, so ideally what you want to have is, ideally you want to have a binding site where all these pieces are all together, and there's a nice pocket. Here you don't have a nice pocket, right? So there is one side of the pocket, but this side of the pocket is missing. You want this flap to come down, like so, right? And so originally, there is no ligand. Much of the molecule is either flexible, pink. Now I'm colorblind, so I don't know which one of this is pink. Maybe this is pink, right? Is this pink?
Yes.
Thank you. So much of the molecule is either flexible pink or somewhat unstable green. Yeah, I'm struggling with green, but maybe here. Okay, few conformations facilitate ligand binding in this low affinity state. But then one ligand makes it. One ligand makes it, this flap closes, and look what happens. This flap closes, but this flap is starting to approach it, right? So this will be an example of positive cooperativity, where the binding of one ligand facilitates the binding of another ligand onto the same protein. Okay, so this flap is coming close. And then the second ligand comes in, and they're both in place. And so so there is much higher affinity now for this ligand toward this protein. So this gives rise to positive cooperativity. Does this make sense? You bind one molecule and you increase the chances that the second molecule will come and bind too. And the reason this happens is because the conformation changes. And it's almost like the binding in one pocket creates another pocket for you. Any questions?
No.
Okay. And so there are two models of this kind of cooperativity. This is still more advanced. It doesn't really do much for us, but it's good to know that actually this can occur through concerted or sequential, right? So concerted, basically, now I think the circles are low affinity states. Hold on a second. So basically, convert it, see what happens. So let's say, so there are two states for this protein, right? So there are four subunits, just like in hemoglobin. 4 subunits can be a circle or can be a square, right? And so when the first ligand binds, what can happen is that all 4 subunits will change shape and adopt the shape of the square. And then continue on. Second subunit change, and then all of them will change the shape at the same time. So basically it's either they all change the shape at the same time or sequentially. So here you can see that actually there are 4 subunits and they all can actually change shape sequentially. So now 3 circles, 1 square, 2 circles, 2 squares, and so on and so forth, right? And so if this ligand binds, it changes into a square, but the other ones can remain circles, or this ligand can actually dictate and tell this subunit to turn into a square. So, so sequential, obviously, there's much more flexibility here, many more possibilities, and this one is simpler. But people have encountered both types of cooperativity. And so, so what we're dealing here is a situation of allosteric regulation. Okay, so allosteric protein is when the binding of a ligand to one site affects the binding properties of a different site on the protein. Can be positive, can be negative, right? So you can have allosteric protein which is homotropic. So the normal ligand of the protein is the allosteric regulator. Can you think of a homotropic allosteric protein? Give me an example of a homotropic allosteric protein. How's this? You see, the ligand is the same for both sides, right? So, so the same ligand that bound here will come and bind there. But if they're different, right? Let's say the two sites are different, and so this ligand will be one type of species, and this ligand will be different type of species. Then this will be heterotropic. Okay, so we just looked at the homotropic allosteric regulator. All right, any questions about anything today?
Oh, would you mind going ahead and making the Unit 5 discussion? And do you know when the homework would be available?
Yeah, I'll work on the homework today. And yeah, you mean the discussion? Yeah, I'll do those two things.
That'd be great, thank you.
And upload the lectures on YouTube. Yep. All right. If you want the chapter 5 discussion, I would like to see you there. Bye, guys.
Thank you.
Bye, thank you.